Greetings and welcome once again to my new calculus channel. My name is John Gabriel, and so in the previous two videos I talked about the uh, epsilon delta definitions, gave you some background, and I gave you 2 points that you were supposed to remember. And in this video I'm going to quickly recap and move on to the third one. So let's begin. So in Why Your Mainstream Calculus is a Load of BS, Part 1 and Part 2, I covered these facts. Okay, so let's just quickly look over them. In other words, this definition here that you find in the mainstream is equivalent to this bogus definition here. So the first problem is that it's circular because L, which is the derivative, is used in its own definition. So that's the first problem. I'm not going to go over anything else on that because I've covered enough on it already. The second problem is that Cauchy didn't really change anything, neither did Weierstrass. They simply took whatever they had in Cauchy's definition and just reworded it without infinity and infinitesimals. And of course, one of the big problems with Cauchy's definition is he says that the function must be continuous, and he assumes continuity. But continuity is insufficient. And why is it insufficient? Well, if we go to a function like this, right, and if these blue lines here are secant lines, how would you find if these blue lines are supposed to be secant lines, which they're not, how would you reconcile the finite differences all along this path, right? So if you start with something like that, let me just get another color pen. Now let's say purple. So if you start off with something like this, then the next secant line would be that, but this wouldn't be a proper finite difference, right? And because these are not really secant lines. So Cauchy really missed something big there. The big thing he missed is that you can only find the derivative using that method on a smooth curve. Okay, so you do need smooth curves because you need secant lines, and these here are not secant lines. So that was one of the big problems with Cauchy's very verbose definition, this one here, where he says if the function y equals to f of x is always continuous between two given bounds, and we choose a value of the variable, etc., there are infinitely small increments, etc., just a load of garbage. So today, what we're going to focus on is, also we covered in the second part that there's no such thing as a real number, and I gave you some material there to study. And in the third part, which is what we're going to focus on today, we're looking at the concept of a verifinition, which is a portmanteau of verify and define. So mainstream academics are quite happy about the fact that they don't have a valid systematic way of finding the derivative because the first principles method is not valid. And the first principles method is indeed equal to the limit definition. They're equivalent, okay? So the limit is being used in its own definition. And so they're happy just to guess L, or the derivative, and then verify it using the epsilon delta definition, which is still the same garbage as what Cauchy gave him, and which Weierstrass just simply rewrote just to save them from being embarrassed and their incompetence and their stupidity and their complete lack of ability. None of them were mathematicians. So any mainstream academic will vehemently claim that a limit is being taken. But while this is partly true, it is, however, equivalent to setting h is equal to 0, which is something they deny. So if we look at this finite difference quotient, it evaluates to the derivative plus some expression in x and h, or a combination of those. But this here is not an error term, as the morons in mainstream think. It is the slope difference, okay? As I've shown you before, f prime of x is just the name we give to the function which produces the tangent line slope at a given point x, and this here is the slope difference. Nothing more than that. There are no error terms, and this is exact, okay? Absolutely exact. And it also turns out that this here is the arithmetic mean, something which baboons of mainstream never knew until I revealed it. The arithmetic mean of all the ordinates of f prime in the interval x to x plus h, okay? So taking the limit of finite differences gives f prime. Discarding q of xh is the same as setting q of xh equal to 0. It's absolutely the same. I mean, you can try it with any example you like. And since taking the limit and setting h equal to 0 produce the same result, it follows that they are equivalent. So we've got nothing else to worry about. So this expression here, let me just write it out actually, once again. Let me write it out. So this expression here this formula, in fact, identity, is my historic geometric theorem. Okay. The historic geometric theorem tells us that the non-parallel secant line slope is equal to the tangent line slope plus or minus some difference. Okay. And you see how this works beautifully in an applet. So for example, we've come to this applet here, and I've chosen the function 1 divided by x to the 4 plus x squared plus 1 for a good reason. And it doesn't matter where you are, you're actually finding the derivative and the slope difference geometrically. Why is that? Because the derivative is f2 over h, and the slope difference is f1 over h. Okay, so you can try all this stuff at home on your own to be able to see why these things are true. And if you're not already a subscriber, become a subscriber. Follow me on academia.edu, click like. Also, remember that I will place links to all these necessary articles and applets, and that in the next part 4, I'll be dealing with another perspective of the same reason why your mainstream calculus is a load of bullshit. So if you're not a special member or a members only, click on any one of my videos, the join button on any one of my videos, and for a mere €4.99 a month, you'll have access to incredible information. In fact, just to give you an idea, this folder here is accessible. The members only folder is accessible only to members. So this folder here will be available only to members. And in there, I share knowledge I've never shared before. And currently, I'm sharing a research project, very important research project, by the way, which is the evolution of number from beginning to end, and many other things, including my theory of learning, which is called CATUS, and it stands for Knowledge Acquisition through Inferential Suspension. So that's pretty much it. I'll be talking to you soon in part 4. My name is John Gabriel, and this is New Calculus Channel. Goodbye.